So, um, how are you? It was nice to see you in November. I hope you're all well. So, would like to tell you this last month, I mean, what is our plan, right? Because we have to see how many days we have and see what to be done. So for this week, for Wednesday and Friday, we'll finish completely finish hardware testing. So there should be nothing left over for that one. And the next week we will cover another, uh, probably at most 1.5 class, and the remaining for 14, 19, 21 will be the regression. So we will done should be done in 2.5 class. So everything will should be done on the within 2 weeks time. And then 26 will be our last class, where we will go over it. We'll do some review, and then probably I'll put up the last year past paper. We'll discuss some of them if we have time. Uh, and then 27 at night, then we will have the exam. Okay. And 28 class will be canceled because I don't think you're interested in doing anything after the exam immediately. But we will do a makeup class on the I think we booked the class on December 1st and 2nd to be a Python tutorial, which is optional. So, I mean, already over exam. So if you want to come, you want to come, because I want to teach some programming languages. If you want to, I mean, that's obviously exam is over. You have already submit your project. So it just for fun if you want to come, but never mind if you are busy because I guess many of you are busy anyway. I look at the past year, actually, very few people would come. Even I have 2 sections. People, I mean, because of the exam is optional, and then no people actually come. But anyway, in case you want to learn, then you'll be good. I mean, I will ask the TA to book the room, but that was the thing. So that would be the plan for the uh remaining. I mean, 1, 2, 3, 4, 5, 6, 7, 8, 7 classes. Okay, we should able to cover everything, so should not be an issue about our progress. Okay, so we said the goal of today would be to finish hypothesis testing. I guess it would be good to review what we have done. I guess because over the weekend it must be the case that it's not easy to remember everything, right? So we'll quickly review hypothesis testing. Hypothesis testing, the idea is closely related to estimation, but a kind of reverse. Estimation is we use the data to guess what's going on in the population, right? Just if you recall, what would be the idea, right? It's just like you have some population. Let's see, the pen can be useful or not, because the pen is always tricky here. It's not working. The population, okay, and the population have many people, right? Our example with Mr. 1 and Miss 2, right? And elderly 3, right? And baby 4, right? So that is our looks like Zumba more than baby, but anyway. So we have four individual here, right? So if this is the only thing in the population, the meal, which is the average, is 2.5, right? And remember, this 2.5 is a number. It's not a random variable because this is a fixed number, right? You just don't know it, but if you know it, it's 2.5, right? But you don't know this number. But you want to guess this number, right? Because maybe this is willing to pay for your product or whatever reason, this is a number you want to guess. and depend on what number you get, right? Suppose you get the Miss 2 and elderly 3, and then actually you get the sample mean, right? Which is again 2.5, right? And that if you used to guess this meal, then you get it right? This is the what we say the estimator, the point estimate. Of course, if you get man 1 and woman 2, then you get 1.5, which is not the accurate guess, right? And we also learned from the last previous several read, right? It will be something like this, right? It will be alpha over 2, sigma over, if you know the sigma, right? And if you assume the population is normally distributed, then you can guess with some margin of error, right? And if you don't know the sigma, you would plus minus Tn minus 1, alpha over 2, sigma over root n, right? So that would be, okay, the pen can be used. And that can be the result, okay, that we are using, right? So that would be the case. And the ideal hypothesis testing is reversely, we have some idea what's going on and go to data to check whether this is support, right? Suppose we say our population mean is 2.5, right? And we look at the sample mean, and the sample mean is exactly 2.5, then we're happy, right? But if it's too big or too small, not sure you want to say yes or no, right? Suppose you're lucky, you got the baby 2 times, right? So your sample mean is 4. So probably we say 4 is too much different from 2.5, right? So you would rather reject it. Or you're lucky, you get the 2 guys, 2 number 1, right? Then you get average is 1. Then we say it's far away from 2.5, right? So it depends on luck, right? That means that for hypothesis testing, you have to decide how much this kind of type 1 error due to sampling mistake, right? Because you can end up with extreme cases all the time. So you would reject at the end of the day, right? So when you do hypothesis testing, you have to specify what's the alpha, what's type 1 error, and then you will decide what are acceptable range, what are unacceptable range, right? And that would be the idea behind. And then we learned 2 things last class. It's called the Z-test and T-test, right? And same as what we do estimation, Z-test is we know sigma square, then we use the Z-test. If we don't know, then we use the T-test, okay? So that's the idea. Okay, let's go to example again because I really want you to know what's going on because as you would agree, okay, hypothesis testing is something that you may have not learned in the high school, right? Because I think you learn estimation if you learn M1, right? So so let me do this two-tail Z-test again, okay, to get a view. So this is a question, you know, the population normal and SD is 4, okay? So usually you don't know this, but let's assume we know it, okay? For some application, we actually have good guess of that, that should be fine. But in general, you don't use this one, use t-test, okay? And we have n is 64, and next bar is 5, okay? So our hypothesis is equal to 6 or not equal to, okay? So by construction, the sample mean is a random variable, right? Because you collect it before you collect data, you don't know where it is, right? Because depend on who you draw. And the sample mean will have the expectation of 6 because that is what you claim. Because we want to test it, so we assume what you claim is true, right? And we know how spread out is this guy because we know the standard deviation is 4. So the variance will be sigma square over n, right? And the SD, of course, will be sigma over root n, right? So that is the if you this is the standard, this is variance, this is standard deviation of this bell curve, right? And next would be our data tell us is actually 5. Okay. So that means that we are here. Okay. Now the question would be, is 5 sufficiently different from 6? Then we say it's beyond the sampling error that we allow, right? In the other words, since our alternative is not equal to 6, so we are saying that we are reserving, okay, alpha over 2, which is usually alpha is 5%, right? So we only allow 2.5% on both sides because you don't know which side, so we do it symmetrically, right? 2.5% on both sides. And if 5 is in this pink region, then we will say it's beyond the sampling error that we allow, then we will reject X1. If not in the pink area, we'll keep it, right? So this idea that how 5 and 6 are different from each other. And we know this based on the bell curve 4 over square root of 64. The SD 4 over 6 square root of 64 is A, right? So this is half, okay? And we know 5 from 6, the distance will be 2 SD, right? Because 1 SD is half, right? So that means that if you convert it to standard normal, right? That means that the red, the 6 becomes 0, okay? And the 5 become -2, okay? Because this is 5 is 2 SD below the mean. Now what is left will be to check out alpha. We use 5% significance level. This is the level that we consider the sampling mistake. And or you can calculate this what is called p-value method, which is calculate this area, right? And this area multiplied by 2, and we compare it to alpha, right? Because this is the p-value method is calculating the alpha we just reject, right? So just changing the alpha such we just got reject, right? Because this area is alpha over 2, so that's why you multiply by 2. So this area, use Excel, will be norm dot s dot this -2 true, okay? And because of this, you multiply by 2, right? So that would be the idea. And you can calculate that is 4%. So if you use 5% as the type 1 error, which is sampling mistake you allow, then you would reject X now, okay? As we say, reject X now as 5. But if you are more strict, you only want 1%, of course, we don't reject. If you're more loose, use 10%, then you also reject as well, okay? And that will be the p-value method, right? So calculate p-value. Or alternatively, as we said, you can use the critical value method, which is you 0 here, okay? And you actually want to calculate this both side area is 0.025, right? Because add up is 5%, right? So for this value will be norm dot s dot inverse. Let me see, I can use the pen. It's a very odd word to write in this way. Can't really write this. 0.025, right? And this guy, right, will be norm dot S dot inverse, okay, 0.975, right? So one will be positive 1.96, okay? The other one will be negative 1.96, right? Because they're symmetric, right? So that would be the idea behind this z-test. Is that okay? So any question? Okay. Let me do a t-test again. Then we'll go to the next review the z-test, okay? So I guess this is one of the most important part you want to learn from this class, because it's to do hypotesting, because there's something that I guess is new to most of you. Okay. So let me do the both tail t-test. So the only difference for this question compared to the previous one is we know it's normal, but we have no idea about sigma square. It's not given from the question. So we don't know sigma square, which is usually the case, right? Suppose I want to know population parameter mu, but of course I don't know sigma. So that will be the case. Of course, you ask, since the t is most common, why we still learn the z? The reason is actually you know when you have large sample size, say n more than 200, actually t value is not much different from the z value. And basically you just replace sigma by s, then you're done. Okay. So that's why there's no harm to learn this anyway. But anyway, let's do it. Okay. So you have to, someone claim your mu is 4. So you want to test this claim. How you test this claim is collect data. Okay. And this data give you, okay. And you want to test against this hypothesis. So what you're doing is, remember, the data you collect is like the bell curve, okay, the sample mean. Because why? Because given by this, right? This is normal, right? So that's why when you collect the data, it's random sample, and it's the average of that. It is still a bell curve, right? And because we think it's 4, so the bell curve will set at 4 as well. Okay. And we know that the way was built, this bell curve is sigma square over root n over n, right? Of course, the variance imply this is the SD, right? Whatever you like, which one. But the problem is we don't know sigma. Okay, so there's a question mark here. But nevertheless, the theory is the same, right? We are saying that we want to see is 4. Of course, the data is away from 4, then we are not very happy, right? So we will again also saying we will reject if it is belong to this area. We decide what it is alpha over 2, right? Alpha is the level of significance, right? It's the level of the type 1 error we like to endure, right? So that is our decision, right? Usually it's 5%. Okay. And the answer, what we get the data is 3, right? It's 3. Okay. We have 3 here. So the question is whether 3 is belong to here or 3 belong to here, right? Question mark. Is 3 belong to the pink area? Of course, you would say 3 is so far away, then you reject, right? If 3 is so close to 4, you're not in the pink area, then you say, okay, no, we keep our H null, right? So that is the overall idea. Okay, so that is the idea. Of course, with no sigma square, we know how spread out it is. We can calculate whether 3 is in the pink or not in the pink, right? So that's not an issue there. The question is we don't know sigma square, okay? So how can we do about that? And we know because of normal, we know S is, then it's okay to consider a T distribution. Okay. And T, the problem is T will have many tables. And we'll use the one is n-1, T15. Okay, this is learned from the last class already, right? Because this is T15. How do you connect T, right? Will be same. Everything will be just subtract from the mean. This becomes 0. Okay. Becomes 0. And how do you, where is the 3 is? Where the 3 is? 3 is the something coming from this expression, right? It's the same as before, right? You're just asking how 3 is different from 4, how many SD, right? And before we use this guy, but now we replace by S, right? So just -1, right? Because it's 1 below as the mean. And this is the SD, right? Coming from this, right? You replace this is S over root n, right? Because now we don't know sigma, right? S is 2, root n is 4, which is 2 over 4, right? It's again is 1/2. Okay. And it's 2 SD below 4, so it's -2. Okay. So that is where the T is. Okay. So easiest to think about this is instead of thinking about whether green is belong to this or outside, that requires to find the critical value. We can do the p-value method, right? Which is calculating what exactly this area and times 2, right? And times 2, then we can directly compare to alpha, right? Because this area is compared to alpha over 2. So what is this area? This area will be just T dot this -2, 15, true, right? So that will be this area. But we just not need this area only, but we need to actually calculate this area as well, because this is what we call the p-value, right? Because we compare this to our alpha, right? Because of course you can compare this to alpha over 2, right? But in general, we define it as the compared to alpha, right? So that's why we multiply by 2 and compare to alpha. And turn out this number is 6%. That means that if you use 5% as the threshold, then you can't reject, right? Because we have this case, right? Actually, we have this case. Okay. So it's not inside the pink region. Okay. So that is the reason why we got this. Okay. If you like, you can do critical value method, which is T15. Okay. Again, 0 is here. Okay. You can calculate this 0.025. Okay. Here is also 0.025. Okay. And you can calculate this critical value will be T dot inverse, okay, 0.025. 0.025. Sorry for my writing because it's not easy to write with a mouse. 15. Okay. And this is T inverse 0.975. 15. Okay. And that turned out to be, you can put Excel, will be positive negative 2.1314. Okay. So that means that our critical region is here. Okay. So this is 2.7 negative 2.713. Okay. So that means that the green line is actually outside the pink region. So you can't reject. if you use the 5%. Is that okay? I just give it for 1 minute before we go to new one. So this is something that I think the review will end here. Let me know if you have any question. Is there any question? Okay. Is that okay? So because you would ask, okay, why we need to learn this kind of stuff, right? First is you often have to do hypothesis testing. Many of you are doing accounting, right? So that is your client or your regulator would actually ask you to check, right? Because you have the inventory, right? Someone claim the inventory like this, you go to the warehouse to pick up something to check. This is something that you actually do in practice, okay? And if you do marketing or quality control, that is actually, you have to do it, right? Because the product, you say so, right? You say this product weighs 1 kilogram, then of course you don't want the government to check it out, then you want to check it yourself, right? Quality control, you pick up something and see whether it is actually 1 kg on average, right? So that is also, you do internal control. The first thing is something, actually the most reason why we want to do this is when we estimate model, which we will do next week about ANOVA and hypothesis testing, and regression, is when we have a model, we estimate some parameter, we want to check those parameter valid. So that's why we will see whether parameter is equal to 0 or not, right? Or valid or not. So that is something that we often check it, okay? And on Friday, we talk about, actually today some will talk as well, is we talk about 2 sample tests, is business we call A/B testing. So we will do that probably after the break. But let's see if any further question before we continue. If no, then I assume it's okay. I think this cohort is very silent compared to previous cohort. They keep asking questions. So, but it's good. It means 2 things. Either you know very well, or either you don't know what's going on, then you don't know even how to ask. But I hope it's the first case, not the second one. But just to remind you, we only have 3 more weeks to go. So if you have any question, please feel free to ask during you reply, or you ask our TA. Okay, so please do that. So a set test on proportion. So in the last class we talked about when estimation. Sorry, I think last week we talked about when estimation. There's a special type of data that help us simplify calculations, binary data, yes, no question. Okay, and very often we do a lot of yes, no question. And when yes, no question, of course, it is not a normal distribution, right? Because yes, no is a Benoni, right? In the population, yes or no, right? But turn out that if look at the yes, no question, the sample proportion, right? It's a random variable. It will still follow normal distribution because by central limit theorem, right? Because no matter what data is, the sample mean is still a you can use a normal distribution, okay? And so that is actually, and also there are another interesting fact to remember is when a binomial, right? When you know the mean, you know the variance, right? Because if mean is A, the variance A times 1 minus A, right? So that is something that you know very well. So also you learn that from previous chapter is if I know the mean, right? The mean and the variance are related in this way, right? The sample, if this population proportion, that A and A minus A. So that means that we can use Z test, okay? We don't use T test, okay? We can always set tests for binary data because that is always approximation is doable, and because under null this is true, right? Because we know the mean, we know the variance, so that's why we can rely on the Z test. Okay, so that is the reason why we also talk about Z test. So let us look at this particular example again. Okay. So we're binary data. Okay. And the random sample of 50 people and sample proportion is 0.5. We want to test pi is 0.4 and pi is not 0.4. So what does that mean? Remember, we are binary data, right? So binary data is bunch of 1 and 0, right? Because in the population, say, suppose I say whether you like, I don't know, Korean pop song, right? And some people say yes, or some people say no, right? And there's one or 0, right? Basically, the data will be, right, bunch of 1 and 0, right? When you actually draw a distribution, right, the P function, right, then will be something like bunch of 0 and bunch of 1, right? The 0 or 1, right? This is the data you would see, right? But this the X, right? But if you look at the X bar sample mean, or actually called sample proportion, right? This is luckily is a bell curve, right? And suppose this is a pi number of people like 1 and 1 minus pi people don't like, right? So that means this pi is here, right? Population proportion, right? And in our example here, we hypothesize 40% of people like Korean pop songs, right? And if you get 50 people, right? You know the spread, right? The spread will be this variance of this bell curve will be pi 1 minus pi over n, right? So this is something that we learned two topic ago. So topic 4, we learned that, right? So that would be actually this number, right? 0.4, 1 minus 0.4 over 50, right? So 0.4, 1 minus 0.4 over 50, right? So we know how spread out is this number, right? So that's good, right? Because we know it's a bell curve, we know where the center, we know the variance, we know everything, right? Because that is normal. Now the data we have is 0.5, right? So we are here, okay, 0.5. So the question again is 0.5 far away from 0.4 so that we say it's sufficient to support x1, not x0, right? So 0.5 is here. So again, the question would be, we have to decide what is our significance level, right? What's the type of error we want to commit? So we add alpha over 2 here and alpha over 2 here, right? Okay. So 2.5 and alpha, we pick 5%, right? So 2.5% on either side. If blue line, which is 0.5, is belong to this orange area, then we would reject, right? If blue area is outside, then we don't, right? So that is whether we keep the H null or not, right? Because we don't see whether H null is right or wrong, okay? Although here I do 2-tail test, actually you can easily imagine if I change H1 to larger or less than, you do the same, right? If larger less than, they just put all alpha on one side, right? But now it's 2-tail, we put alpha 2 on both sides. So now the question is whether blue is in this orange or not, right? We know it's bell curve. So that means that we can use the Z to do it, right? Because looking at how many SD are below the mean, right? So 4.4 with 0. So 0.4 with 0 here. Okay. And what's 0.5 here? This is 0.5. 0.5 here go down, right? I'll do it. Will be the distance is 0.1. 0.1 over square root of this guy, because it's SD, right? It's 0.1, just basically this number, right? It's negative 1.44. Sorry, it's positive 1.44. Okay. So 0.5 become 1.44. So this 1.44 SD above the mean, right? So that's what the 1.44 means, right? Because we standardize normal. Standardized normal means you try to see how far away from that. So what we're going to do is look at this area, right? And of course, symmetrically look at negative 1.44, right? Look at these two areas, add up together. Is it more than alpha or less than alpha? Because this area is what we call p-value, right? P-value is the value such that you adjust the alpha, you just got this reject. Okay. And how to calculate this p-value? This p-value will be norm, because bell curve, right? Norm dot s. Okay, this Excel input, but of course you can check the T table, but that's easier. Norm dot s dot this, because you want to find area, and 1.44 true. Okay. And remember, this area is left-hand side area, right? Because this is a this. So 1 minus will give the area on the right-hand side, right? So that's how it gives you the purple 1 minus. Okay. But you need 2 times of it. So it will be 2 times 1 minus area. Okay. So that is how we get this area, and turn out this area is 14%. You can put in the Excel, you can just plug in. I'm not going to do that, but you can try this at home, right? Or anytime during the break. I mean, to try during the break, I guess, if you have time, it just take you 1 minute to do it. And this is 14%. So that means that this is too large, right? Because this can be just due to sampling error, right? Even though the data is 0.4, 40% of people like pop song, then it's easy to end up with 0.5. Okay, it's not conceivable every 14%, 15%, right? It's end up in this number. Okay, so we will not reject this. We keep this guy. Okay, we will not reject this. We keep this guy. We keep x0. So that's how you test this, right? So you want to test whether it's less than 0.4, not less than 0.4, or more than 0.4. Then it's how you test this hypothesis. And again, you also want to do the p-value method. This is done, right? But sometimes in your textbook, they want to do what we call the p-value critical value method, right? This gives you the z, right? This is 0, right? And of course, we know if we want this to be 0.025 here, 0.025 here, right? We know our old friend well enough how to calculate this, but let me write that down. Will be normal dot s dot inverse 0.025, right? This gives you negative 1.96. Okay. If you do this guy, this number will be norm dot s dot inverse 0.975, right? This will give you 1.96, right? And 1.96 will be, of course, inside this region, right? Because this is 1.44, 1.96 is bigger than 1.44, right? So that's why we can't reject it. Is that okay? So we can't reject it because 1.96 is the point of no return is the rejection region, right? And 1.44 is not in the rejection region. So you are not going to reject H null, you keep H null. Okay. Is that clear what we are doing? Okay. And send a question before we proceed, because we're done with the t-test and the z-test. So this one sample we're done already. Okay. So there's nothing. I mean, basically, we are done with all the basic theory of statistics for this class. From now on, we'll focus on application. So after the break, we'll do the A/B testing. We give you two samples. We try to compare and contrast. Okay. For example, A/B testing will involve like you want to compare, say stock A and stock B. You want to look at the return. Say, is stock A have higher return than stock B, right? Or your marketing example is A/B testing is you want to sell this through this marketing campaign, marketing channel, right? Retail channel, maybe online. The other is offline. You want to see online will sell more than offline, or the vice versa, or the same, right? So you have data on online, data on offline. You compare which channel will do better. Actually, because by sampling mistake, right? You can one way or the other. So you want to compare two things. Or you have some what we call more in-depth of comparison is comparing whether people take vaccine, right? Some people before the vaccine and after the vaccine, whether they recover faster or not, right? There are many cases. We call A/B testing, okay? And that will be covered after the break. Okay, so basically, if we were to learn the t-test and the z-test, basically we've done all the theory part. Okay, and after work, we're basically doing all the application. For this one, okay. If there are no further question, let's have break earlier so that we resume a little bit earlier. So we have break 3 minutes earlier, so we resume at 11:28. And at the meantime, I guess we should do the you reply. Okay, so I leave here. In case any question, just feel free to ask me because it's closer to the end of the semester. I guess you have a lot of questions might be in your mind. So I have a break of 15 minutes. Let's resume at 11:28.
我哋想係，因為佢係講緊question。我呢啲 accessory 攞嚟做手術，調研佢。係咪使俾我哋？咩計出嚟呢個？我係人都未識啦，即係話，可以。未主嘅呢個係呢個度㗎，亦都係。You guys know that well, yeah. That's perfect. 你想玩到？如果佢係呢度上，呢度係我哋應該講咧，即係話擺咁啊，因為你係呢個係個嘛，咁應該你換得嚟出嚟。喺邊度出嚟？你乜嘢幫我？即係第二個。即係喺 email 佢講話你可以40塊。但係佢做咩？呢個馬上就翻。4個嘢，反正我唔知個位嘅。上到上佢未呢個嘢係咪先都好低啊嘛？呢個低啊嘛，係咪？呢個可能就係3分。係有 risk 㗎，呢個就係得人打撈先係。有咩對付啊？就係特別因為佢擺上去，然後我哋就上嚟，跟住後面因為問題嗰幾個10多嘅啫。哦，我覺得係啱，我都講嘅。咁佢一個口啊，好仔。我而家就 period 咩？咩嘅？你係一個咩？一個咩？咁就點樣爆？係嗰個 party room 啫嘛。即係見到啲咩？你唔好同我講翻單，我講點樣 measurement 總之就話要整個 measurement 之後俾個 result。個 measurement program 幾字 page 簡單即係我搞到你。今日嗰份。今日嗰份我翻嚟嗰份幾大，我都知道，識下啦呢個。哦，我哋嘅地圖咧，即係如果1、4、10真係啊。但係因為呢個9嘅，喂，但係呢個兩個數齋就冇理啦。萬一你個咩上插咗啊？俾佢邊走咗屌！插咗啊！萬一佢話做 ACC， 我邊望下我 ACC。佢上嚟我俾你，你嗰陣時冇同我哋啊？咪對咗咯。你自己坐親啦，叫我坐得你。係好似你做完之後又唔鋪啦，你鋪啊嘛。3鋪。嗱，首先你自己標咧，都冇咩下邊啦，真係唔好意思，我哋條件OK，但係咩唔使 check 啦？今朝早咧，我係有個以上完咗，未必啊。Accounting 嘅 project。
啊，希望 Cherry 可以就之後見到成個都笑之後卡手嘅收面出嘅時候，懂嘅，我佢哋如果好嘅，可能會被派面派咗教。你影相出咪同佢分，但係我覺得都算應該都係變幾個數字，即係話有4個。十個音樂，真係做漏笑啦。做 DOTE 嘅比例上就幾多人幾個小牌掟佢出嚟，有啲分題。呢個唔係 random variable，單係個數字。但係要自咁知佢要幾多出嚟 guess 佢，俾人 guess 佢咪就係先。今個禮拜教。因為咧，我你有加啲，你快啲自己花死估你啦！得啦，我收啦。可以 table 可以揾到嘅嘛？我俾你可以揾到嘅路尾，table 俾單 Excel 嚟嘛？有個 detail 但係冇99咯，我都冇99，係咯，100咯，係咯，咪199。知道佢寫錯，即係寫翻嘢打錯，
你有冇打錯？如果你哋冇打錯，
最尾嗰啲打錯。
呢
個我俾你噶嘛，我話試下佢咪錄啊嘛，問係咪錄機？呢個係好明，你睇到下同埋差唔多，但唔係你交完埋真係就佢變出嚟。咁應該 suppose 我諗應該係做一份生，做一份生文做本來做一份嘅，不過我諗嗰份就 up 咗。即係我哋得翻份，咁你哋一份咧少啲錢數喎。我應該 set 啲。不如我咁多年都冇人發現呢個寫錯。我係第三。多謝你寫我，咁多年冇話我寫錯，不過你知道係咩嚟嘅？不過 P.B.A 改啦 ，P.B.A 我夾硬都解釋到。係知點樣咧？一樣嘅。喂，但我哋份佢得成係咪？有個字俾咁跌咗個係咪嚟㗎？係咪？係啦，係咁啦。你哋考完交出去啦。呢個應該咧，我哋話我哋個科啦係嘛？所以睇下上啲。我哋頭都冇講。有問題或者 I 嘛？係咯。人嘛 AI 有問題啊？支持你啊！我有個導手，知道什麼 set test， 如果唔知佢做唔知道做咩，即係基本上你日常生活中就係 TTS 啦，除非你係 proportion， 我識啲就係 set test。即係個攞出嚟係假設，即係一定我哋5%作為 bench， 你可以零分嘅，你自己中意嘅，或者10嘅就得，你自己中意嘅就睇下。咁啊，即係別再但係有啲包就係係咯，喺入邊即係晚上你自己講，俾你係有咩問題？我真係冇嘢咁衰，真係好衰嘅。 因為收入減翻個 variable cost，佢減翻個 fixed cost 咯。咁啊，即係等於收入係減個 cost，減個 variable cost 同埋 fixed cost。
我哋話如果問點解係咪 personal experience 嘅話，問一個全關係，係佢
我 skip 咗。flexible 就係 A 係啊。我有個 friend 用 AI 嗰個，
你之前有提
我係要用完即係，我唔會 A 嘅，真係。講嘅呢啲你想印個飯都得，印到個人太粗㗎，好處係你揾一次啫。對幾多？
我想講，因為我喺上年就嗰度俾4方8年鬧緊，跟住我做嘅事情少到咁，然後這個都得趕緊，這個什麼時候要去嗎？那這個就我媽落咗對，我媽落。
我真係有試過，但係呢個情況，我係咁嘅情況，呢個俾人 test 出嚟嘅，即係佢就某一次佢，test 就唔知點樣，我我呢個難，我覺得難啲咯。
So I hope you're well. How many more homework will release? Okay. By construction, there actually will be 2 more homework, but I noticed that many of you are actually very busy. So probably we will just skip 1 homework, but I will still put it on the web and you can try to do it. I will release the answer automatically. So the very last assignment, I will skip it. So we only 1 more homework. So basically the 1 more homework will be the hypothesis testing will be our last homework. ANOVA regression, I will put the question there and release the solution later. But you can try to do it. Of course, if you're too busy, you can just do it on your own schedule. But that would be the case that I want you to do it. So just 1 more assignment, but do note that the assignment is very useful to make you work, because the assignment is very fundamental, and I'm pretty sure that if you try to put it in the AI, then actually you will get the answer very quickly. But I do recommend you not to do it. I mean, of course, if you really cannot control yourself, put in the AI, at least you try to check if the AI is right or wrong. I mean, right? But I really can't see you whether put an AI or not, right? But I hope that you don't use it, and you are also allowed to talk to other classmates, right? So I think it's best to learn together. But of course, submit your own answer to that. So Chair, Oh, I really forgot what the mean chair means. It's a very tired. It's very competitive, or I forgot the meaning. Is it very busy? I think it's something like that. I mean, I don't understand the meaning of this. So let me go there again. So what does that mean? This means the following. Okay. Remember, well, why this comes out? Why this comes out? Remember what you're doing. It's like this. Okay. Your hypothesis is 0.4 supposed to be here. Okay. And 5% is the thing that we this is the level of the error we accept, right? Because even this is true, it can be anywhere because it's normal, right? So we said that this add up together 5%, so it's 2.5% here. Okay. It is the thing that we would say 0.025, right? This is the area in the red region. If it's this will be far away from 0.4, right? Because it cannot be 0.4, but how far from 0.4 you would reject. What do we mean by 0.1498? Is actually your data is 0.5 is here, right? 0.5 is here. Okay. What is said is 0.5 is here. You this area, and this is actually 0.3. Okay. These two green area add up together is 14%. Okay. 14% is the joint green area. And if this green area is more than the sum of red areas with 5% of threshold. So this p-value, right, is more than the alpha. That means that you will say this can arise due to sampling mistake, right? By 14%, actually, we can have that. So it's not small enough to rule out that you get 0.5 is just by accident, right? By sampling error. It's not small enough to rule out the sampling mistake. So we will not reject H now. We will keep this one. Okay, that's what I said here. We fail to reject H now. So we will keep H now. Okay. If this green area is small, less than 5%, is very small, right? Then we will reject H now. So that's the idea, right? It's because we are saying how far away from 0.4, right? If this area is very small, then it means it's far away from 0.4, then reject. So that's always this idea behind. Okay. So you can see the idea is not complicated. Is there any question? No? Okay. But if you have a question, ask again, because we're actually doing the same again throughout this week. Oh, midterm tonight is already okay. I'm sorry for you because I already end of semester, but midterm. I guess it's not midterm, it's final, right? I think it's final. And then you have presentation. I guess it's a final. I guess some of the teachers like this, right? Good. Okay. How well you're doing? Just to remind one of you, today is Wednesday. First day, your day off. Happy for you, and then you can celebrate your congregation ceremony with your friends. So it's not today yet. What's the weather? Windy, sunny. Okay, that's okay. Key point, many. C test for binary data, yes. Yeah, I think you know very well about what we're doing. Speed wise, it's okay. At least no one say 2, but I hope it's not too fast, not too slow. And so not that it is okay, but I think we will. Oh, still we see more than half of people still retired, which is you are more tired compared to other section. I think other section less than 50% are super tired. So unfortunate fact. Lastly, let's see whether you have jokes to share. So hello and hi, one day collide to each other, they fight. Who will win? Who will win? Hi or hello? I don't know. What is the answer? Oh, Halloween. Okay. I see. That's Halloween. Okay, that's a good one. Halloween. Okay, that's okay. No. Next Friday driving exam. Oh, good luck for you. Well, I can't say too much about driving because in the US it's very easy to drive, but I can't pass the exam, so I can't really drive legally in anywhere in the world because I didn't pass the driver exam. So so there's something that you guys are better than me because I don't know how to drive. So good luck for your driving exam. But anyway, I don't need driving anyway because I always live in city. So oh, why was the computer cold? It left its windows open. Okay, that's a good one. Happy day. I missed the bus to see you and was late for 30 minutes. Sorry for you. In case you miss it, I'll upload the video. I mean, as usual, so you can check out the recorded lecture to see what kind of thing you missed. Final Wednesday. Yes, middle of the week. So I hope you're okay. So now we are going to talk about two samples. So basically, this is the application we have covered. Okay. So don't worry. There is not, basically, there's no new knowledge, but we just adopt the principle we learn. And of course, there's some new formula, but overall, it's the same thing. Okay. So let us talk about two samples. Okay. Forget about the last one. The last one is comparing variance, okay, which is something new. And the first four situation is still comparing means, okay? And the first three situation is comparing means in different situations, okay? But before we do that, let us consider the first case, okay? What we call independent sample, okay? And very often, we're actually comparing two situations. Remember, maybe we compare two different products, okay? How well they're doing, how people want to spend on them, right? Or compare performance of two managers in two cities, right? Or comparing two different retail channels, so on and so forth, right? So we often be comparing two things. So the idea is we will have two bell curve, and then that is what we do. So let us look at the notation. I spare you from reading this. Let me do a whiteboard to describe what's going on there. So what we get is like this. Okay, we'll have a population 1. Okay, you can imagine that may be a bunch of girls, right? That's why I use red color. Okay, population 1, maybe a bunch of women, right? And this is woman number 1. Okay, and woman number 2, so on and so forth. Number 1, number 2, right? Number 3, and so on and so forth, right? And many of them. And this, we assume the distribution is like a bell curve. Okay. This is called X1, right? And this mean is called mu1. and the variance is called sigma 1 square. Okay. And we will do sampling, right? This means that if you collect sample number 1, we get from here, maybe one guy there, we'll call it X11. Okay. And if you do a second one, will be X12, so on and so forth, right? The data we got is X11, X12, so on and so forth until X1N1, right? So N1 is the number of the sample we got from population 1, right? Remember, these X11 up to X1N are all random variable, okay? And of course, that means that you can have what we call the sample mean, X1 bar, okay? And X1 bar also will bell curve, right? And the mean will be, again, mu1, right? The variance will be sigma 1 square over N1, right? So that would be the idea, right? Of course, you can also calculate S1, which is the sample variance, right? By calculating all the difference, right? X1 minus X11 minus X bar 1 square, okay? Add up all together, divided by N1 minus 1, right? This is the sample variance. And remember, this is a good guess for this guy, right? So that is what we have, right? So we have a bell curve, right? We'll collect some data from these women's, okay? And we have N1 of them. And remember, they're all random variable. And the sample mean is averaging out. Also is a bell curve, right? And also a sample variance. This is a good estimate for the population variance. So this is nothing new, right? We learned that already. And the new thing here is instead of 1 only, we have another population 2, bunch of boys, okay? Bunch of boys here, right? Bunch of boy number 1, so on and so forth, right? So you have the population mean mu2, sigma 2 square, okay? You also have the sample mean, you collect data with sample mean 2, right? The data you have is X21, X22, right? And so on and so forth, X2, N2, right? And this guy is also a bell curve and everything the same, right? So that is the idea, right? You have 2 bell curve. So what we are going to do in the hypothesizing is the following, okay? Is we want to know, for example, many people do gender study, right, these days, right? They worry about the gender gap, right? For example, care about how men are earning are different from women's earning, right? So we want to see is the mu1 is same as mu2, right? So that's the, usually you go to gender study, the first thing they test is like this, right? Is mu1 equal to mu2, right? The same or not, right? Or is woman will be willing to spend more on a product than a man, right? So that would be the question, right? And of course, the alternative can be anything you like, right? Maybe depends on what you think, right? Can be mu1 bigger than mu2, can be mu1 less than mu2, right? Or mu1 not equal to mu2, right? So that is something that we want to see, but it depends on what is in your mind to test. Okay. And remember, how we're going to test is the following. Okay, how are we going to do this? How we test this guy? What we're going to do is do the following. Remember, X1 bar is like this, right? It's mu1 sigma 1 square over N1, right? And X2 bar is mu2, right? They are both bell curve, right? And remember y over n1n2, because when you collect more data, the bell is strings, right? So if there's law of large number, when n1 go to infinity, that's shrink to nothing. So how you can test this hypothesis? Mu1 equal to mu2, right? Okay. If they are equal, what does that mean? It means the following: x1 bar minus x2 bar will be set as 0, a bell curve. Remember, the bell curve, the difference is still a bell curve, right? And because mu1 equal to mu2, it will center as 0. Okay. And the variance will be mu1 square over n1 plus mu2 square over n2, right? That is what we learned in the chapter 3, topic 3, where your two bell curve, if they're independent, it is the subtraction is still a bell curve with the mean of the difference between their population mean, but the variance add together, right? So this is what you learn from previous chapter, right? So that is the main goal of here, right? So again, that will be our hypothesis testing, right? Suppose later you will see, suppose we consider this standard case not equal to, right? That means that if your data is, you put alpha to here, right? Okay. If you know sigma 1 square and sigma 2 square, if you collect the data x1 bar minus x2 bar is in this region, the red region you reject. If not, then you do not reject, right? So that is very simple. Okay. So it's easy if you know sigma 1 and sigma 2, right? So everything is trivial. There's nothing new to learn there because it's same as before. Sorry. So what is new thing to learn would be if you don't know the sigma, right? If you don't know the sigma, then you have to use sample variance S1 and S2. And in that case, you have some new formula to do. That's what we'll do. Okay. So you have to be very careful. If you don't know this, you use the T table. Okay. And which T table to pick up will be different. Okay. Depend on assumption. So the new thing is you replace by S, you have to check out which T table to do. So that will be the tricky part we will discuss today and on Friday. Okay. So let's go back to the slide. This is overview what we're doing. Okay. So let's look at this again slide. So we have the population of mean mu I and sigma I, and this is data we already said. And this is what we call the sample mean. Just to remind you that these sample mean are all random variable. Okay, so these are all. These are all random variable, so that's why you have expectation. Okay, that's the bell curve idea, right? Remember, sample means the bell curve, and the sample variance are unbiased estimator. So that's we know it already. There's nothing new here. Okay, and if it's normal, then everything is normal. So that's our assumption. Okay, so this is something we said before. If you're two bell curve independent, the difference is still a bell curve, right? So that's we said in the whiteboard. We just write down there. It's bell curve, difference is still bell curve, right? There's nothing new here. So as I said, in the application will be you compare two stores, sales manager, which is better, which product is better, or which vaccine is better, right? So now the thing will be how do we proceed, right? If we solve this problem, okay? So first we will consider a case today is to do it in a special case, okay? A special case we will assume is we assume this is true, okay? And you ask, how can we show this is true? We'll do it on Friday, which is called F test, which can see, you can test whether this is true or not, okay? So don't worry at this moment. Let's consider this is true, okay? And Friday, we'll talk about the case this is not true, or if time with today. So assume the same variance. Don't remember what it is you can imagine if boy and girl are very similar, then probably it's okay to assume this is the case, right? Or you assume product A and B are maybe just different color, right? If you have you don't think these two things are different, then you can make this assumption. Okay. Just to remind you that when we do statistics, we always making assumption where you are aware or not. Okay. So this is not too crazy assumption. Okay. Now, first, why this assumption helps? Because if you recall, how can we estimate this guy? We can estimate this by S1 squared, right? You can look at the data of from sample 1, we use the sample variance of 1 to estimate this. And we can also use, we will use S1, S2 square estimate this guy. Okay. And since they're same, that means that I can use S1 to get this, and also S2 to get this, right? Anything actually will be good, right? S1 square or S2 square will be unbiased estimator, right? Or anything combined, right? You can use half of S1 square and half of S2 square. Or 30% of S1 square and 7% S2 square will foot the bill, right? It doesn't really matter. Any combination will work, okay? You take half of S1 square and half of S2 square will fit. But the problem is everything is unbiased. Remember how to guess besides their bias is called efficient, right? Smallest variance, okay? Turn out that if you use this formula, this will be the best guess. The proof in the slide, but I'm not to prove it, okay? But let me show you why this is, to see why this is a good guess, okay? You will see this is just basically weighted sum, okay? And you can see denominator the same, okay? And you can call this A, this is B, right? You call this part is A, this part is B, right? This is A over A plus B. This is B over A plus B, right? So this is just weighted average, right? With S1 got weighting A and S2 get weighting B, right? And why you give this such a weighting? Remember, if you have a lot of data on 1 rather than 2, okay, put it in this case. If A population 1 and 2 have same N1 and N2, right? If N1 equal to N2, okay? If N1 equal to N2, this will be half and half, right? Because if you have the same, then these two can give you the same information, right? You just use half of S1 and half of S2 with the best guess. But what if you have a lot of data on population 1, but not a lot of S2, right? That means the N1 is very large compared to S2, okay? That means that you want to use more variation data on 1 rather than 2. Right? So that's why A is large compared to B. So the end result SP square will be tipped towards S1 over S2. Is that clear what we're doing? Okay. So this SP square will be the most efficient estimator. Okay. So you remember you can any way you combine S1 and S2 is good. Okay. It's unbiased, but it's not the most efficient. And the most efficient one is combined based on sample size. If you have a lot of data on population 1, a lot of things from girl, you should use girl as the estimate the variation, right? If the equal number of boys and girls, then you get the same number, right? Half and half, right? If you have more information on boys, then you can use more boys. Is that clear why we are doing this? Okay. Of course, if you don't get it, this is the formula there. Okay, you don't have to worry too much about it. It's just the formula. Okay. Okay. So, I guess let's see the example, and you will see how we do it. Okay. So here it is. Okay. So under equivariance, this is the formula, right? So this is something we know that the same. This is the bell curve. Okay. And you use SP to get sigma, right? So we just over this standard D of this guy and look at the T. And the T is the degree of freedom is N1 plus N2 minus 2. Okay. I'm not explaining why this is the case. But basically because you guess X1 bar and X2 bar. So that's why you minus 2, right? If you know mu1 and mu2, then you don't have to minus, but that would be the idea behind. But I guess it's good to just look at the result. Okay. Okay. Before we do that, let me talk about this as well. It's what we call the interval estimator. Okay. And if you want to say how much woman want to spend more than men, this will be the point estimator, right? Just take the difference of the sample mean, right? Will give us how much woman will spend more than men, right? This is the point estimator. Okay? And if you assume they have the same variance, this will be the interval estimator, right? Because you remember this is Tn minus 1 alpha over 2, right? And S over root n, right? So this is the same thing here, but just change to this one. Okay. I guess a little bit too much formula here, but let us go to the example, then hopefully I can convince you that this is nothing very difficult. Okay. So now let me open the whiteboard, okay, to convince you the example, for example, that is something not difficult. Yeah. Now let's see the question. The question said the following. We have two populations follow the normal same variance with two bell curve or same size. Okay. And we collect the data from population 1, sample size 50, sample mean 40 and S1 4, another random sample from another population, sample size is 40, sample mean is 42 and S2 is 3. So you want to test whether the same or not. Okay. So let's see this example carefully again, but let me write down the what we have in the question first. Okay. We have N1 is 50. Okay. X bar is 40. And S1 is 4. Okay. And we have the blue here is N2 is 40. X2 is 42. Okay. And S2 is 3. So this is the question. Okay. And we want to test the following. H null mu1 equal to mu2. Okay. And X1 will be mu1 not equal to mu2. Okay. And what you're doing, remember they're all bell curve, right? So we know that actually we're saying that the following, right? This is X bar normal, X bar 1. Okay. You have mu1 here, a bell curve. Okay. And this variance will be sigma square 1 over n1, right? This is what we have, right? And we also have x2 there from the woman, so the man, right? With mu2 here, because also bell curve, right? Would be mu2 square over n2, okay? And under the null hypothesis, we said they're same, so they just have the same here, right? So they're the same, right? So if you really want to plot it out, it will be something like this, right? It will be something like x bar 1, x maybe here, right? X bar 1, right? Maybe somewhere mu1 is something like this. And maybe I use the red color, right? Maybe use red color. X bar 1, right? Something like this, right? And then we have X bar 2, also somewhere. They may not have same variance, right? Because depend on sample size, right? And also depend on sigma 1, sigma 2, right? But they all have centered it at the same location, right? It's equal to mu2, right? So they are all two bell curve. That means that if I have x1 bar minus x2 bar, right? Under this scenario, you will set at 0, right? And the curve, the variance will be x sigma 1 over n1 plus sigma 2 square over n2, right? So this is what we learned, right? So, right? So basically, this is the bell curve, right? So this is basically same as one sample test, right? We know the difference between the sample mean will be a bell curve, right? Follow this bell, right? There's no different from one sample test, right? Because one sample is just, I tell you sample mean follow a bell curve. But now I tell you the difference of the sample mean will also follow a bell curve, right? So the first thing to do here will be because, sorry, we said sigma 1 equals sigma 2, right? So we assume sigma 1 square equal to sigma 2 square, okay? Equal to sigma, okay? Some number. And in this particular case, we can use the formula called SP square, okay? And this is the most efficient estimator for sigma, okay? And this will be, the formula will be something S1 square and something S2 square, right? And it's a ratio, right? And it will be N1 minus 1, right? It will be N2 minus 2. And since it's the weighted average, so it's adding up the two numerator, right? So you can just plug in the number, which is 49, okay, over 88, okay. S1 square would be 16 times 39 over 88 times 9, okay. Should be some number between 12, okay. So it should be some number between 16 and 9, right? But turn out to be something like 12, okay. It's more closer to 16 rather than 9 because you have more data on population 1 over population 2. So 16 is more accurate than 9. Okay, is that clear? So if you look at data, it tells you that x1 bar is 14, x2 bar is 42. So actually we are here, -2. Okay? Because this is 40 minus 42. So the question is -2, is it far away from 0 or not, right? And of course we want it, as we said, we want it to be like this is alpha over 2 here and alpha over 2 there, right? So we want to see whether this -2 belong to the pink area or not, right? So that is the idea, right? If belong to the pink area, that means that it's far away from 0, right? And the problem, as I said, is we don't know sigma. We have to use the S, right? So how can we use S? So it will be something like this, right? We will, instead of, we look at T, and from the formula is N1 plus N2 minus 2. So it's T88. Okay. And 0 is here. Okay. And what should be -2? Okay, this -2 is what number? Okay. This you would do is -2 minus 0, right? This number will be -2 minus 0, right? This is how you calculate, over square root of this guy, right? Square root of this number SP square, right? Will be SP square over N1. N1 is 50. Okay, it's 12 square over 50 plus SP square over 40. Okay, so that would be the number here. Okay, and let's look at the number we calculate from our slide. The number is, this number is -2.6. Okay, so this is actually -2.65. So we want to see, is -2.65 far away from 0, so that we say X now is not true because it's too far away from that, right? So what we're going to do is to calculate this p-value, right? And this area multiply by 2 and compare to 5%, right? So that would be, how to calculate that? This will be T, this, pre-doc this, right? -2.65, 88, true. And you multiply this by 2, right? So this is the area you compare to the alpha, right? This is the p-value, the p-value, right? P-value. Okay. If this is less than 5%, then we say, okay, it can't be sampling error, right? It must be the case that actually X now is wrong, right? If it is more than 5%, okay, it can be just X now is true, but due to some sampling mistake is there, right? So that is the idea. Is that okay? Is that okay how we do the calculation? And if you look at the slide, what is this Excel input? The answer would be, let's see. The answer is like 0.01%, right? So this area is 0.01. Okay. That means that if you use the 5%, then you would say, okay, it's 1%. It's so small. It's so far away from 0. Then X now cannot be true, right? We'll reject the man and woman have the same population mean. Okay. So that's the idea. Is that okay? Is that okay? Okay. So lastly, other than this this method, right? We can do the critical value method. Let me go to the next slide, right? We can do the critical value method. Is the following, right? We'll do TATA, right? And we go for that, right? We ask ourselves, this is 0, right? We want this to 0.025. And this is scan is 0.025. Okay. What's critical value, right? How do you find this number? This number is T inverse 0.025 ATA. And this number, according to the slide, is 1.97, or you can should be negative 1.987, or you can do this number because it's T inverse 0.975. Some of you asked me in the break why this 0.975, because the inverse is looking at the left hand side area. So the right hand side is 0.025, the left hand side is 1 minus 0.025 is 0.975. Sorry, 88. You can try this at home for the Excel. Within 19. Okay. And remember our data, what's number they give is 2.6, right? Negative 2.6. So that means that our data is actually somewhere here, deep inside the region, because it's negative 2.6. Okay. Right. So that means that we will reject this hypothesis. Is that okay? Okay. Lastly, if you don't want to do hypo testing, you also will have to do interval estimate or estimate, right? If you have x bar 1 is 40, okay, x bar 2 is 42, right? So what is the guess? You want to guess mu1 minus mu2, right? What's the best guess? The best guess for this will be just x bar 1 minus x bar 2, right? This is the best point estimate. This will be negative 2, right? So you want to guess how much women want to spend than men on average with negative 2, right? Because this is coming from the data, right? The point estimate. Because women want to spend $40, men want to spend 42. So the difference is $2, right? So that is the best guess you can guess. It's a point estimate. But if you want to guess better, you can have interval estimate, right? Will be x1 bar minus x2 bar plus minus t n1 plus n2 minus 2 alpha 2, right? And we have square root sp square over n1 plus sp square over n2, okay? And this is negative 2, okay? And this guy, we figured already, is 1.987. And what is this guy? This guy is our denominator here. This guy, right? Our denominator. So you can get this number, and this number will be right here at the end, right? Is here. This number. Okay. So that would be your interval estimate. So suppose you want to guess how much men and women different spending. So this will be interval. You only guess midpoint with negative 2. The whole interval with this one. Okay. So I don't want to spend more time because I'm over time by 1 minute already. So don't worry. We'll revisit the example again in the next class on the Friday. And we'll finish the rest of the thing in the Friday. So enjoy the weekend. For those who have midterm tonight, good luck. I see you on Friday.